In this first of a three-part tutorial, we will be talking about CAN bus communications. This is of intermediate complexity, designed for those with some knowledge of computers and electronics. For this, we will be using a benchtop test setup of some modules from a Tesla Roadster, connected via 4 CAN buses and powered by a 12 volts bench power supply. Let's look at the modules. Here we have a OVMS, which is the main computer, an instrument cluster, a little visual display screen, and 4 CAN buses that connect together all the different modules in the car. It is common to have multiple CAN buses for performance and to separate critical systems from those less important. We'll use our multimeter to measure the input voltage coming from the bench power supply. Seeing roughly 13 volts is fairly common for 12-volt based systems. Now let's look at the voltage on the CAN bus connections. Each bus has 2 signal wires called CAN low and CAN high. Compared to the system ground, on the first bus we are seeing around 2 volts on CAN low and 2.8 volts on CAN high. The second bus is showing about the same, while the other 2 are showing around 2.5 volts on both wires. The difference depends on things like whether the bus is active or not, and termination arrangements. This is expected. The CAN bus is a differential bus, with the difference between the 2 wires interpreted as the signal. When idle, we would expect 2.5 volts on both wires. When active, the high line goes to 3.75 volts and the low 1.25 volts, leading to a differential of 2.5 volts. Let's use an oscilloscope to look into this in more detail than a simple multimeter can allow us. So here we have an oscilloscope connected to our test bench. We've connected the first channel, colored yellow, to the CAN low wire of the bus, and the second channel, colored blue, to the CAN high wire. The oscilloscope plots the voltage levels on each wire over time. We have voltage on the vertical axis, and time on the horizontal. The bus is running at 1 MHz, so that is 1 million cycles a second. Far too fast to see anything useful, so let's pause it with a single snapshot. Now we can see the data much clearer as the signal's binary 1s and 0s are represented by high and low voltage levels. This digital oscilloscope captures up to 2 billion samples a second, and this allows us to zoom in to get a much more detailed view. We can see the 2 wires are mirrors of the signal. When one is high, the other is low. This is so that any interference, increasing or decreasing the voltage on the wires, will likely affect both equally. Remember that we are only looking at the differential, the difference, so that should be unaffected by such interference. Each CAN bus should be terminated with resistors at each end of the bus. This helps to minimize reflection of signals and allows for high data rates and reliable communications. In very short buses, such as our test bench setup, this is not so important, but correct termination is essential with longer wire runs in electrically noisy environments such as vehicles. With this digital oscilloscope, we can go further and configure it to actually decode the CAN bus data from the electrical signals seen. For this, we only need to look at one signal line, and we've chosen and configured for CAN low. Let's turn on the decode so that we can see the data as annotation under the waveform. We can also turn on a table to show us the messages seen on the bus in a more human-readable format. Looking at the decoded data, the first item we see, highlighted in dark blue color, is the ID. This identifies the message type, and also by convention the sender of the message. In CAN there is no specified recipient as this is a broadcast system. We can see ID 400 and 100 in hexadecimal. Next, in yellow, we have the data length. For basic CAN this can be between 0 and 8 bytes. Then, in green, are the up to 8 bytes of data. And the message completes with the pale blue checksum which can be used to detect unintended corruption during message transmission. In the decode table we can see ACK to indicate that this message has been acknowledged. Every CAN bus must have at least 2 nodes, with the transmitter being notified of correct transmission by the acknowledgement sent by one or more actively listening nodes on the bus. It is a common beginner mistake to try to build CAN buses with just one node for testing. Also beware that nodes can be configured to behave like this oscilloscope and merely listen on the bus without actively acknowledging transmitted messages. The message ID is important as it not only identifies the origin of the message but also the priority. As many nodes may be transmitting on the bus at the same time, they need some way of detecting clashes and prioritizing traffic. The ID does this as when nodes transmit they also listen on the bus for other nodes transmitting their ID, and if they find such traffic, with early bits in the higher priority ID appearing first, then they back off and try again later. While digital signal oscilloscopes such as this provide excellent visibility into the CAN bus signals as well as basic decode capabilities, they are not really suited to in-depth analysis and reverse engineering. For that, it is better to work at the message level with CAN bus loggers and analysis tools. Let's now look at how OVMS can help us with this. Here we have an OVMS module connected to both Wi-Fi and the CAN bus of our test bench setup. Let's connect to its console using SSH. Now we start the CAN bus in active mode at 1 MHz speed. Take care to get the speed correct, as active mode with the wrong speed will mess up the bus. If you don't know the speed, you can first try and listen only mode without danger. We can check the status to see the received message count increasing. Now we will configure OVMS as a CAN logger to help us to look at the data. We can start as a monitor, to show messages on the console, TCP client to send to a remote listening TCP host, UDP client to send to a remote listening UDP host, TCP server to allow remote hosts to connect to us, or VFS to save to OVMS virtual file system, such as to SD card locally. Let's use TCP server to allow our workstation to connect to OVMS. Next we choose what to do with data coming from the network. We can discard it, simulate it by feeding the messages to OVMS, or transmit it out on the CAN bus. Now we choose the format of the log files to be produced. For this case, we are going to use the text-based CRTD format. Lastly, we specify the port for connections. Let's now use the Netcat tool to connect to the OVMS CAN bus logger on the TCP port 3000. See the CAN bus messages in the CRTD format we configured. The CRTD format has time in seconds and microseconds as the first column, then the message type. In this case bus number 1, receive data, in 11-bit standard format. Then the message ID, and data bytes. Let's reconnect, but this time using the T command to also save the data into a file on our local file system. You can use whatever local tools you are comfortable with for doing this. It is simply a textual TCP stream. Once we have the data logged locally, we can do whatever we want with it. There are many tools available for Windows, Mac OS X, and Linux, for comprehensive analysis and decoding of such CAN bus logs. Let's look at one such open-source cross-platform tool called SavvyCAN. This can both read OVMS CAN log files in CRTD format, as well as directly connect to OVMS over Wi-Fi using its own data format. Similar to last time, we are going to start a TCP server CAN bus logger on OVMS. But this time we are going to use SavvyCAN's own binary format as the protocol, and listen on TCP port 23. Launching the SavvyCAN program, we will bring up the connection manager and add a network connection to OVMS. Once the connection has been established, the CAN bus messages start to stream into SavvyCAN. Let's have a look at what SavvyCAN gives us. First is the message history display. It shows each message in a similar way to what we have previously seen. It also gives us a nice summary table of all the unique message IDs seen on the bus, and we can filter by turning on or off the display of each message type. Then it has a large number of reverse engineering tools available for signal analysis. Here we can look through the sequence of messages for one particular ID and look at which bits of the data are changing over time. We can also perform detailed analysis of the data frames. See a histogram of each byte, showing all the value seen, and try to start to identify the meaning behind the data. It is not uncommon for CAN messages to be multiplexed, with one particular byte being an index for a sub-message type. For the Tesla Roadster instrumentation CAN bus, both ID 100 and 400 use the first byte as just such a multiplexer. In such systems, the meaning and interpretation of the remaining bytes of the message is dependent on the multiplexer byte, so identifying such multiplex data is often the first task in reverse engineering a particular CAN bus. SavvyCAN also has the ability to transmit or play back messages on the CAN bus, although obviously such an approach needs to be taken carefully so as not to interfere with other vehicle systems. We can also load previously saved log files into SavvyCAN for offline analysis. For example, let's load our previously saved log file in CRTD format. We've obviously only briefly introduced the capabilities of SavvyCAN, working in conjunction with OVMS as a CAN bus logger. We encourage you to visit the SavvyCAN site for further detail. In part 2 of this series of videos we will look in more detail at the analysis of broadcast data CAN buses, and in part 3 we will look at OBD2 and the request-response style protocols to retrieve PIDs. Thank you for listening.